Alright, grade 11s. Today what we're going to be looking at is the limit and what that means and what it implies in terms of a function and the rate of change of a function or the gradient of that function. Alright, this is new language. It's new terms that you're going to have to get used to. And the more you use them, the more you're going to get used to them. Alright, so expressing limits in mathematical language, we say that a limit can be used to describe the behavior of a function, so the function's name is f of x, as x approaches a certain value, say a. And in some cases, our function actually can't be defined at a. And the nomenclature, or the way it is written, looks like this. So the limit as x approaches t is equal to 10t. Okay, we read that as the limit of f of x as x approaches t is equal to 10t. So let's have a look at kind of what we mean by that. So if we look at the behavior of our function, a really simple one, x plus 3. Okay, so f of x or y is equal to x plus 3. And we want to see what happens around about the point where x equals 2. Okay, so if I took a value at 1.95, that's kind of close to 2, and I make x equal to 1.95, then my f of x, or my function, will be 4.95. Okay, and what about if I take it at the other side? So I'll now go at 2.05. Alright, so that's 2.05 plus 3, and my function is equal to 5.05. Alright, so that's 0.05 away from 2 on either side. What about if I moved closer to 2? So now we're going at 0.01 before 2 and 0.01 after 2, so 1.99 and 2.01. Well then, if I put that value for x in, I'm going to have 1.99 plus 3, and that gives me 4.99, and 2.01 plus 3 gives me 5.01. Notice that 4.99 is closer to 5 than 4.95 is, and 5.01 is closer to 5 than 5.05 is. What about if I moved even closer to 2? All right, so now I'm looking at 0.005 on either side of 2. My value of my function would now be 4.995, and from this side it's 5.005. So as you can see, as I make my value of x closer and closer to the value at 2, my values of my function, my y values, my f of x, is getting closer and closer to a value of 5. Now we can use the same sort of approach to get an idea for the gradient of our tangent. So remember yesterday when you drew that tangent by hand, everybody's gradient was a little bit different. Okay, but if we draw chords, okay, so this chord from P to Q, and then I draw a chord from P to Q1, and then a chord from P to Q2. If I make those chords smaller and smaller and smaller, okay, or shorter and shorter and shorter, and I find, remember, a chord is just a straight line, right? And I can find a gradient of a straight line, okay? So you can see that the gradient, I'm going to maybe write there, of the chord, because we're actually talking about chords there, gets closer and closer to the gradient of my tangent at point P if I make those chords shorter and shorter and shorter. The main thing to know is that we actually cannot make our chord equal to 0, okay, because then you've got only one point and you can't find the gradient of a straight line at one point. So we're saying it approaches 0, all right? And we have this like really, really, really tiny change, and we're going to call h our really small change, okay? That's really, really tiny, because we can't have it exactly at the same point, but we can have a really short chord. All right. So let's have a look at how that works. So this picture over here, we're actually looking under a microscope. That's how small that's how small our change or our length of our chord is. Okay, and let's give ourselves some points. Okay, so this point Q, our x value will be x plus h, and our y value will be f of x plus h. Okay, so that's the coordinates of our point Q, and our coordinates of our point P will just be x and f of x. Okay, now if I make my chord short enough, hopefully what I'll get is that my gradient of my tangent will be very, very similar to my gradient of my chord. Okay, so now h is getting extremely close to 0 without equaling 0. So how we would write that is we would say the limit as h approaches 0. Now we're talking h being this distance over here. Okay, the distance between x and x plus h. All right, and to calculate the gradient of our tangent at P, remember gradient of a tangent is rise over run, and that's equal to y2 take y1 over x2 take x1. And our y2 in this case is going to be at our q, so it'll be f of x plus h minus, and our y1 is f of x over x plus h minus x. Okay, and that's going to be f of x plus h minus f of x over h. Your x's cancel. Okay, and our new concept that we're then learning, or what we would call this, is that f dashed of x, or the derivative, is the gradient function of f of x. And it's important to realize that this is another function. It's a gradient function. Okay? This process of finding the gradient function using this method is called differentiation from first principles. And that's kind of the key words to see when you read that in an exam or in any question that's asking you. If they're asking you from first principles, you are expected to go through this process, okay? Or finding the derivative from first principles. Now, there's also new notation that you have to learn, and all of these are equivalent to each other, and you need to be able to use them interchangeably. So you can be asked, given f of x, find f dashed of x, or given y, find y dashed, or given y, find dy by dx, and we actually call that Leibniz notation. This notation is read as the change in y with respect to x, f dashed of x, y dashed, and dy by dx are called derivatives.